Hey pre-cal class, Mrs. Levenseller here. Just leaving you a quick video so that you can work on assignment 4. And I'm starting in the vocabulary exploration, so if you can take that out and pause the video while you get it out. And then scroll and find end behavior. We're going to fill this in. This completely filled in version of the vocabulary exploration is also on Schoology in your Unit 2 folder. So please feel free to look there too if you would like to. So two things we're going to talk about today, end behavior and extrema. So I'm going to start with end behavior. And this is really related to limits when you get to calculus. It's one of the first things you'll do when you begin calculus, hopefully next year. So it's important you understand the concept of end behavior. So let's read through this piece. For the definition, the end behavior is where the function values lead at either end of the graph. So where the function values lead at either end of the graph. Whenever I talk about function values, we're talking about the y values, okay? On the right-hand side in facts and characteristics, these are two examples of how you're going to write the end behavior. So the beginning will always be the same and you'll have two versions. The first will be as x approaches positive infinity. And so if we're thinking about a graph here, right, on the x-axis as x approaches positive infinity will be everything to the right of that graph. So everything here is as x approaches positive infinity. Whereas if we want as x approaches negative infinity, we're really looking for anything to the left. So as we go to the left of our graph, what's the function doing? As we go to the right of our graph, what's the function doing? When you get into calculus, this will change into being the wording of a limit. So it'll say as the limit of x approaches infinity, what does that equal? That's the same thing that we're saying here. Okay, so we're going to use this notation every single time. And so if we look at this graph here, when I look at this piece of graph, the first one I'll do is as x approaches negative infinity. So as we're going to the left of our graph, as x is going to the left, what is the function doing? Well, the function is going down to negative infinity, right? So the simple way of saying that is on the left, we're going down. On the right-hand side, as x is approaching positive infinity as we go to the right, my function is going up. So on the right, we'd be going up. And so I would write that as x approaches negative infinity, f of x is also approaching negative infinity. That little arrow means approaching. And then, so that takes care of the left side of the graph. As x approaches positive infinity, so as we go to the right side, f of x is also approaching positive infinity. Right? So that's the formal way to write your end behavior. A more informal way, which when we start to talk about polynomials and graph polynomials, I'll be fine with you guys just saying, okay, on the left we go up, and on the right we go down. But the more informal way is to just have arrows showing which direction your function is headed. I would like us to stay away from that, and because we're analyzing the functions, stick to the more formal aspect of writing the end behavior for now. Okay, so when you see end behavior, left end behavior is talking about as x approaches negative infinity, right end behavior is as x approaches positive infinity. That's what those two pieces are discussing. And we'll do an example in a little bit that'll help you out. For the next piece, go ahead and find your minimum and maximum. All right, again, these are probably things you talked about in Algebra 2, but just a refresher on what they really mean. And you might not have discussed in Algebra 2 that there are actually two kinds. So the minimum and the maximum, those definitions are really closely related, but they're opposites. So we're going to talk about two kinds of minimum values here. And the plural of minimum is minima. So if we're going to find the minima, that just means more than one. Minima and maxima together are called extrema. So you'll see the title of your assignment is to find extrema. That's the minimum and the maximum. So there are two types. First is a relative minimum, which means that it's a point that would be lower than the points directly beside it on either side. Okay, so it's the lowest point in its own separate little area. Doesn't mean it's the lowest point of the entire function, but it's the lowest point in its own specific interval. An absolute minimum is the lowest point on the entire graph. All right, and so if our graph goes to negative infinity, then there won't be an absolute minimum, right? Because there's no way we can actually pinpoint one number that would be the smallest number if it goes down to negative infinity. A couple key pieces of information. There can be multiple relative minimum because there can be multiple places where your graph is lower than points on either side of it, but there can only be one absolute minimum, all right? And an absolute minimum could also be considered a relative minimum. There can only be one because it has to be absolutely the lowest. There are two other words that sometimes people use to describe this, and that will be local and global. And those words mean the same thing. So if I say local or relative, those are interchangeable. Absolute or global, those are interchangeable. All right. When you're finding the minimum value is the y, the actual minimum. So if I ask you for the minimum, you're looking for the y value of your point. But the location, how we describe where it is, will be the x value. Just like we do with increasing, decreasing intervals, we talk about it with the x values. So let's take a look at this picture here. So we have this function, and right here I see a spot that it is lower than the points directly on either side of it, right? So it's lower than the 2 points directly next to it. So that makes it a relative minimum. Same thing over here. This point happens to be lower than the points directly on either side of it, so it's another relative minimum. And same idea here. This point is lower than the points directly on either side of it, so it's a relative minimum again. When I look at that graph as a whole, the lowest point we have altogether is over here, and so that would be your absolute minimum. All right. And when you write the minimums and maximum values, you're talking about where they occur. So we would say here we have a relative minimum at -3, 1, and 4. Those are the x values where those occur. We have an absolute minimum at -3. If I ask you what the value is, then you would tell me the y value, which I didn't really show you that on the graph. But if I ask you just where it is and if we have one, you're just telling me the x values that they occurred on, okay? And over here, just an example, this would be an example of a relative minimum because it's the lowest point on either side, but it's not an absolute minimum because this guy is going down to infinity. So there are points lower on this line than this point would be here, okay? All right, and similar thing for the maximum value. Everything is just the opposite, okay? So again, we can have a relative or a local. We can have an absolute or a global. And if the graph goes to positive infinity, then there is no absolute maximum. Plural of maximum is maxima. There can be multiple relatives, only one absolute. Location of the maxima is always the x, but the actual value of the maximum is the y. And same situation here. This and this are both relative minima because they're the highest point, or sorry, not minima, maxima, because they're the highest point on either, next to the points on either side of them, they're the highest. This one is also the absolute maximum because it is the highest point of the whole entire function. All right. And then over here, we would have this point would be a relative maximum because it's higher than the points on either side of it, but it's not an absolute maximum because we're going to infinity. All right, so that takes care of our vocabulary exploration. So now, take out the assignment that you were given, and let's take a look at just this first example here. So you can sort of fill in some of this information as we did in the vocabulary exploration. Absolute max and min is absolutely the highest or lowest point of the function. A relative max or min is a point on the function that is higher or lower than the points directly next to it. So we're looking at a certain interval where there would be one point that's higher than all the rest. And so keep that in mind really when you're starting to look for max and min on a graph, because it can get trickier if it's not a nice smooth polynomial. Finding a max or min value means finding the y value, or the function of the point, but we'll say y. And the x value helps you locate the point, but is not the max or min value. All stuff we just talked about. So here, if we look at this graph, they're giving us an example. They put this into their graphing calculator. We want to find the coordinate points of the extrema. All right, so we're looking for a maximum or a minimum value. So let's talk first about relative mins. So I'm going to go over here and I'm looking at my graph. This looks like a lowest point in its area. This looks like a lowest point in its area. This would be a relative minimum, and this would be a relative minimum, but also an absolute minimum because it's the lowest point on the graph. Okay, so we would say we have a relative minimum at maybe -2.5, and also 4.1. So relative min at x equals -2.5 and 4.1. And then the absolute min would be at x equals 4.1. All right. If they wanted relative and absolute max values, let's go ahead and look at our graph again. I see this point is, I'll do that a different color. This point is higher than all the rest, so that would be an absolute, or sorry, a relative maximum. And is this the highest point on the whole graph? No, because we're going up to infinity on both sides. So that point is a relative max, which is happening when x is 0, but it's not an absolute. So relative max at x equals 0, but no absolute max. And then what is the minimum value of the function? It would be, if they're asking for the minimum, they're asking for the y value. The lowest point here is where x was 4.1, so I would say about -59, approximately. If you actually were using your graphing calculator, you could be much more exact about this. Okay. So let's talk here about these three examples. Here we have a piece of a function. Well, it is a function, but we're really seeing this one piece it ends. And it has a closed endpoint. So when I'm looking here, two things are happening. I have this point here, which is lower than the points on either side of it. So that would be a relative minimum. But this one here is kind of interesting. It's lower than a lot of pieces around it, but it's also higher than the points directly next to it, right? It's higher than the point to the left, and it's higher than the point, there's no point to the right, so it's higher. So this would be a relative maximum where that endpoint is, okay? So relative min at the bottom of that curve, relative max at the endpoint. The difference between 2 and 3 is over here you have this open circle. There's no one value I can pinpoint there, right? There's no real number that I can pinpoint that's going to be higher than the one next to it because that's an open circle. So in this case, this one is not a relative max because there isn't a point on either side that I can really pinpoint. We can get really, really close to that open circle, and we have an infinite amount of numbers leading up to that. So I can't pinpoint one value that's going to be higher than the one on either side of it. So when I can't do that, we would just say there's not a relative max, but this guy down here would still be a relative minimum. Could we consider this the absolute minimum? I want you to think about that. Is there any point on this function that is lower than that base point? No. So that would be also an absolute min. Oops. And same thing over here, absolute min as well. Two different names for that one. And the third example, we have an open endpoint and then a closed endpoint above it. So thinking about, all right, here is a little dip or valley, and that is still a low point on the graph, but because I have this going to negative infinity, it's not the lowest anymore. So this is a relative minimum. And then when I look up here, I have this point, which is a closed circle, and that is higher than the points directly to the left of it and directly to the right. It's not the highest overall because we're also going to positive infinity, but because it's higher than the points directly to the left or the right, it's a relative maximum. Right, so those can get a little tricky there. So let's talk about putting all of this together here. So here's number 5, here's a function. And the first thing I want to do is look at this and put it into the graphing calculator. So I've gone ahead and done that, I think. Sorry. Oh, I guess it's gone. 0.5 times x squared plus 1 times the square root of 4 minus x. Okay, so there's that function there. On your graphing calculator, if you're not using Desmos, you might not see part of it that's going down to where 4 is, but that's just because of the pixels. Desmos shows you really the whole thing. So we can see we have from 4 and everything to the left of 4. So if I were to write the domain, we're going to say that we have everything from 4, negative infinity, up to 4. So that's my first piece here. And I'm including 4 there. If we looked at just the equation, we could prove that by saying, okay, well, there's a radical, and nothing under the radical could be negative. So we'd say 4 minus x is greater than or equal to 0. Add x. So 4 is greater than or equal to x, or x is less than or equal to 4. Right, so that's the algebraic proof of that. There's no division here, so I don't have to ever worry about dividing by 0. So that takes care of my domain. If I can't divide by 0, then there are no vertical asymptotes and there are no holes, right? So think back to the last assignment that we did. If anything cancels, it's a hole. If any factors cancel, if they don't cancel and they're in the denominator, it would make a vertical asymptote. Now I want to go look at the max and min values. So I'm going back to my graph. So absolute max and min. I have 2 points that could be considered minimum. We have the point 0, 1, and we have the point 4, 0. All right. The absolute min would be 4, 0, right? When x is 4. And 0, 1 would be a relative minimum. All right. So those two values would be the minimum values. So absolute would be at when x is equal to 4. The min is 0. And the local min was when x is equal to 0. The minimum was equal to 1. All right. Going back to my graph and looking for a maximum, I have a point here. So 3.1, oops, sorry, trying to get rid of that point. 3.1 and 5.0. So that would be a local maximum, but it's not the absolute because this graph continues to infinity. So at x is 3.1, we have a relative max, and the max is 5. And there was no absolute max because it goes to infinity. All right. Now let's look for increasing and decreasing intervals. So it's going to start, it increases from here all the way down till we get to that 0.01. I'm having a hard time getting right on it, but 0.1. And then at 0.1 it increases from 0.1 to 3.1, right? And remember, we're always talking about the x values here. So we're decreasing from negative infinity all the way up to 0. And then we increase from 0 to 3.1. And then we are decreasing again from 3.1 to 4, right? And it stops at 4. So 3.1 to 4. All right. So then the last piece here is the left end behavior and the right end behavior. So as my graph goes off to negative infinity, so as x goes to negative infinity, the function is increasing, right? So the function is getting larger. So that'll be my first piece, the left end behavior. As x approaches negative infinity, f of x is approaching positive infinity. For the right end behavior, as x is approaching positive infinity, f of x is approaching, so as I go in the positive direction of my graph, here we're going, it ends at 4. Nothing goes past 4, right? So as we are going to positive infinity, the function is going to 4. Or sorry, the y value, we'd use the y value here, so the function is going to 0, all right, and it stops at 0. And you can sketch the graph from Desmos there, but that would be the different information for this particular function. So what I would like you guys to do is to try below on the practice numbers 1, 2, and 3. See what you can come up with for those values. If you finish, you can try some of the other ones, 4, 5, and 6, or you can also go back and brush up on your factor